Hello there. Let us continue solving questions on iteration statements. And in this video, we will solve these 4 questions. By the way, I've already solved 17 questions across 2 different videos. And if the list of questions seems interesting to you and you have not watched those videos yet, you can check them out by clicking the card that must be appearing in the top right section of your screen. So let's continue and let's get started with the first question from the list, which is given an integer x and an integer n, we need to find x power n. So before we write code for this, let us understand how we can solve this using pen and paper. Now we are supposed to find x power n and we will be given x and n, right? So x power n is the same as multiplying x n number of times, right? So if I say 5 power 4, for example, it is multiplying 5 4 times, right? So what will we have to do is, given n, we will have to ensure that we are getting x n number of times, which we can do with the help of a loop, right? So if I say for I equal to 1, I less than equal to n, I plus plus, and let's say all I do is just print x over here. What will we get? We will get 5 printed 4 times, right? Which means this loop is capable of giving us 5 4 times. Now, what we have to do is we have to multiply 5 4 times, right? So for that, what will we have to do is we will have to, first of all, take a variable called product. We will have to initialize this to 1, right? And then in the loop every time, this is what we will have to do. We will have to multiply product with x and we will have to store it back in the same variable, right? So if we do that at the end of the loop, when we print the value that is stored in the variable product, we will have 625, considering that we are taking x as 5 and n as 4, right? So this code will help us in finding x power n, right? So with this clear, let us go to IntelliJ and let us start writing the code. So the first thing I'll do is expand src and then iteration statements and then questions. And inside this, I will create a new package first. And I'll call this package as mathematical underscore loop underscore patterns. And here I'll create a new Java class with the name q1 underscore find x power n. And I'll have a main method. Now over here, I'll need 2 variables, x and n. So let's take x and initialize this to 5. And in the next line, let's take n and initialize this to 4. Now, on the basis of whatever we have discussed, what will we have to do is create a variable called product, initialize 1 to it, and then iterate how many times? N number of times, right? So we will say for int I is equal to 1, I less than equal to n, I plus plus. And then we will say product is equal to product multiplied with x, right? And at the end of the loop, we will print the value of product. And with this, we should be able to get x power n. And since x is 5 and n is 4, we expect 5 into 5, which is 25, and 25 into 25, which is 625 as the output. And that is what we are getting, right? And if I change the n to 3, I should get 125. And that is what we have. Let's take another example. Let's say x is, say, 3. And let's take n as 5. So 3 power 5 will be 3 into 3, 9. 9 into 9 is 81. 81 into 3 is 243. And that is what we have got. So this code seems to be working perfectly fine, right? Now over here, I'm assuming that you understand why did I initialize product to 1 and why are we going for product multiplied with x and storing it back in the same variable, which is product. But if you don't, I would recommend that you take a look at these 2 videos and not the entire video, but just take a look at how I have solved these 2 questions. That is this one, given a positive integer n, find sum of all numbers from 1 to n, and this one, that is, given an integer n, find the product of digits of n. Understanding how I have solved these two questions will tell you why did I go for initializing product to 1 and then this statement, which is multiplying product with x and storing the result back in the same variable. So with this done, let's come back over here and let's mark the first question as completed. And with that, let's move on to the next question, which is given an integer n, find all divisors of n. So again, before we start writing code, let us think as to how we can solve this using pen and paper. And for that, let us take n and let's assume that it contains 20. So if n is 20, we are supposed to find all the divisors of 20, right? So if you were to solve this using pen and paper, that is, if let's say you had only 20, as in we are not considering programming as of now, we are trying to solve this using pen and paper. So if you had only 20 and you were supposed to find all divisors of 20, what would you do? You'd start from the first number, which is 1, right? And then you would check if 1 can divide 20 completely or not. And when I say divide 20 completely, what I mean is 1 can divide 20 and leave 0 as the remainder. That is what we mean when we say something dividing something else completely. That is, the remainder is 0, right? So we would check if 1 can divide 20 completely or not. And it can, right? So we will treat this or consider 1 as one of the divisors of 20, right? Then we will move on to the next number, which is 2. And we will do the same thing with 2. That is, check if this can divide 20 completely or not. And it can. So we will consider this as another divisor of 20. And we will do the same thing with 3. But 3 cannot divide 20 completely, right? It will leave 2 as the remainder. So 3 is not a divisor of 20. Then we will continue and take 4 and 5. And both of this, that is both 4 and 5, can completely divide 20. So 4 and 5 are also divisors of 20. Then we will continue and take 6, 7, 8, and 9. And none of these can divide 20 completely. But 10 can, right? So we will take 10 as another divisor of 20. Then we will continue and take 11, 12, 13, 14, and 15. And none of these can divide 20 completely. So none of these are divisors of 20. Then we will take 16, 17, 18, and 19. And again, none of these can divide 20 completely. So none of these are divisors of 20. Then lastly, we will have 20. And 20 can divide 20 completely, right? So 20 is another divisor of 20. So with this, we will have all the divisors of 20, right? And they are 1, 2, 4, 5, 10, and 20, right? So how did we solve this over here? Over here, what we did was, given 20, we started from 1 and went all the way up to 20, right? And then for all the numbers between 1 and 20, and of course, including 1 and 20, we checked which of them can divide 20, right? And all those numbers which could divide 20, like 1, 2, 4, 5, 10, and 20, are the divisors of 20, right? So if we were to translate this to code, what will we have to do is, we will first of all have to get all numbers from 1 to 20, right? And now, since we are talking about code, let us introduce a variable, say n. So given n, we will have to ensure that we can get all numbers from 1 to n, right? And that is something that we already know how to do, right? We can do that with the help of a loop. So we will say for I equal to 1, I less than equal to n, I plus plus, right? And this loop would give us all the numbers from 1 to n with an increment of 1. What I mean is, it will give 1, and then 2, then 3, and then 4, then 5, and so on, all the way up to n, right? So the first step is clear. First step involves getting all the numbers from 1 to n. Now, what are we supposed to do next is, we're supposed to check which of these numbers can divide n. In this case, 20, right? So for each number, we will have to check if we divide 20 by that number, will we get 0 as a remainder or not? And that can be done easily with the help of this expression, which is n mod I equal to 0, right? N is 20, I is, let's say, 4. So we will check if I divide 20 by 4 and collect the remainder, will I get 0 or not? So this check is something that we will have to do, right? So let us introduce that as well, as in, let us write the if block over here inside the for loop. So we'll say if n mod I equal to 0. Now, if we take a look at this condition, there can be two cases. Either this condition is true or this condition is false, right? So if the condition is false, that means the current value of I cannot divide n completely, as in it won't give 0 as a remainder, right? But if it is true, it means that the current value of I can divide n completely, as in give 0 as a remainder. And that is the value of I that we are looking for. So if we get such a value of I, what will we have to do is we will have to print it, right? So what are we going to do next is introduce a println statement which prints the value of I inside the body of if. So this code will help us in iterating from 1 all the way up to the value of n. Then for each value of I that we will have in the loop, we will check if we divide n by that value, if we will get 0 as a remainder or not. If we get 0 as a remainder, we print I, because getting 0 as a remainder means that the current value of I is a divisor of n, right? So that is why we will just print the value of I. So this is how we can solve this question using code. So with this understood, let us come back to IntelliJ and let us create a class first of all. Let's name the class as q2 underscore print all divisors of n. And what are we going to do next is we're going to have a main method. Now inside the main method, we will first of all have to take a variable called n and let us initialize this to 20, right? Then on the basis of whatever we have discussed, what will we have to do is we will have to iterate from 1 all the way up to n. And inside the body of for, what will we have to do is we will have to check if n when divided by the current value of I gives 0 as a remainder or not. If it does, it means I is one of the divisors of n, right? So we will just print the value of I. Now, if I run this code, what do we expect? We expect 1, 2, 4, 5, 10, and 20 as the output, which is what we are getting, right? If I change this to, for example, 24, what do we expect? We expect 1, 2, 3, 4, 6, 8, 12, and 24. So let's run the code and check. And we are getting 1, 2, 3, 4, 6, 8, 12, and 24. Now let's change this to 35, for example, and let's see what is the output that we get. So we expect 1, 5, 7, and 35 as the output, right? And that is what we are getting. So this code seems to be working perfectly fine, right? Now, although this code works fine, there's some optimization that we can do to this. To understand what kind of optimization we can do, let us come back over here. And here, let's take a few examples along with 20. So for 20, what did we get as the output? We got 1, 2, 4, 5, 10, and 20, right? So let us put that down quickly over here. Similarly, for 24, we got, and for 35, we had, right? So take a look at these numbers and their divisors and tell me what you observe. Well, one thing you would observe for sure is each of them has got 1 as a divisor, right? So let me mark this for now. Each of them will have 1 as a divisor for sure. Then another thing you would observe is for each number, the number itself is one of its divisors, right? So let me mark that as well. Now, on the basis of whatever we see over here, can we say that for any given value of n, we will have at least 2 divisors, that is 1 and the number itself, right? Because at least for the example that we have taken, this seems to be holding up, right? So on the basis of that, we can say that for any given value of n, 1 and n will be its divisors. And it makes sense, right? Because 1 can divide any number and give 0 as the remainder. And the same thing applies to a number getting divided by itself. If we do that, we will get 1 as the quotient and 0 as the remainder, right? So if we take any value of n, we need not check if we can divide n by 1 and n to get 0 as the remainder, because we know that we will, right? So if we come back to the logic that we have discussed over here, we are iterating from 1 going all the way up to n and checking if each of them can divide 0 or not. And the ones that can is getting printed, right? And in this process, we are checking for 1 and n also, because we are starting from 1 and going all the way up to n, including n, right? But we have just discussed that we need not do it. I mean, doing it is not a problem, of course. We have just seen that the code is working absolutely fine. But then there is no need to do that, because this would be true every single time, right? So the optimization that I was talking about involves not checking for 1 and n. And now if we were to do that, if we don't want to check for 1 and n, what will we have to do? Well, if we take a look at the code that we have over here, we are starting from 1, then going to 2, then 3, and then so on, all the way up to n, right? If we don't have to check for 1 and n, we will have to ensure that we don't start at 1, right? We start at 2. And we will also have to ensure that we don't go all the way up to n, we go up to n minus 1, right? So in short, we will have to modify this loop if we have to skip checking for 1 and n, right? So let me write the modified loop over here. So what we will have to do is we'll have to start the loop from 2 and we will have to go till n minus 1. And that is why I'm saying I less than n, right? Then we'll have to increment this by 1. And then the body of the loop will be the same. That is, if n mod I equal to 0, what will we have to do is print the value of I, right? So this modified loop will ensure that we don't check for 1 and n. But there's another problem that we have introduced, which is if we come back to the previous code, since we are starting from 1 and going all the way up to n, 1 and n is also getting printed, right? But over here, if we don't start from 1 and start from 2 instead, and if we don't go all the way up to n and go up to n minus 1 instead, this code will not be able to print 1 and n, right? But 1 and n should also be printed, right? So how can we handle this? We can handle this by printing the values 1 and n either before the for loop or after the for loop, right? So we can say system.out.println 1, and here itself we can say system.out.println n, or we can put two system.out.printlns over here and we can print 1 and n, right? Or what we can do is we can print 1 first, then let the loop run, and then finally, once the loop is done, we can print the value of n. So you can choose any way, but what I will do is I'll go with this, because if we go with this, what are we going to get is we're going to get 1 first, then all the other divisors, and then n. So the output and the order of the numbers that we get, that is the order of the divisors that we get, will be the same as the previous one. So that is why let's go for this. Let's first of all print 1, then run the loop from 2 to n minus 1 and print any divisor the value of n might have. And then lastly, let's print n. So with all of this discussed, let us go to IntelliJ and let us implement this. So for that, the first thing which I'll do is I will rename this class and I'll say q2 underscore print all divisors of n underscore solution 1. And let me copy the name. Let's refactor. Then let's create a new Java class and let's name this as q2 underscore print all divisors of n solution 2. And here, what am I going to do is, first of all, grab the main method from question 2 solution 1 and let's paste it over here. Then according to whatever we have discussed, we will start from 2 and we will go all the way up to n minus 1, right? So if I run the code at this point, I will get only 5 and 7. And that's what we are getting, right? But then we also need 1 and 35 to be printed. So I will print 1 over here and I will print n at the end. So if I run this code now, I get 1, 5, 7, 35, which is what we got when we executed this code. So let's just run this for once and check. And we are getting 1, 5, 7, and 35, right? So this is how we can optimize the first solution a little bit. Now, even though we have optimized a little bit, there's room for more optimization. And again, to discuss that, let us come back over here. And first of all, let me erase all of this because this is not required. Now, let me come back to this and ask you the same question. What do you observe? Well, we have done this exercise already, and we observe that each of them has got 1 as one of their divisors, and each of them has got the number itself as one of the divisors. But do you observe something else? Well, take a look at 20 first. What is the last divisor that you are getting? The last divisor that you are getting is 20, right? What is the second last divisor that you are getting? It is 10. Now, let's come to 24 and let's observe the last divisor. The last divisor is 24. And what is the second last divisor? It is 12, right? So if we take just this into consideration, what do you observe with the second last divisor that we have? The second last divisor in both these cases is half of the number that we are dealing with, right? So for 20, the second last divisor is 10. For 24, the second last divisor is 12, right? Now, let me first of all make some space over here. And let's see if the same thing holds for 35 also or not. So for 35, the last divisor is 35. But the second last divisor is 7. And 7 is not 35 by 2. 7 is 35 by 5. But what are we dividing with is not important. What I want to do is draw your attention to the fact that the second last divisor is either the half of the number or is less than half of the number, right? So if the number that we have taken is an even number, the second last divisor would be half of the number. But if the number that we have taken is an odd number, like we see over here, the second last divisor is less than half of the number, right? So can we generalize this and can we say that if I take n, the first divisor would be 1, of course, then there would be a few more divisors, and then the last divisor would be n, right? But if we talk about the second last divisor, the second last divisor would be either n by 2 if it is even, I mean if n is even, or it will be less than n by 2 if n is odd, right? Now, what does that tell us? That tells us that no matter which number we take, either even or odd, between n by 2, that is from n by 2 plus 1, all the way up to n minus 1, there is no divisor, right? So what I mean here is, if I take 20 as an example, between, 20 by 2 plus 1, which is 11, and 20 minus 1, which is 19, none of the numbers will be able to divide 20, right? And something similar would hold for the cases where n is odd. So if I take n as 35 and I apply the same thing over here, what will we get? So 35 by 2 plus 1. Let us take this as 17 plus 1, which is 18. So between 18 and n minus 1, which will give us 34. So between 18 and 34, none of the numbers will be able to divide 35, right? I mean, there are more numbers which cannot divide 35 before 18 even, but then we are trying to generalize it. So generalizing, we can say that if we take n, and irrespective of whether n is even or odd, none of the numbers between n by 2 plus 1 and n minus 1, and including both, of course, can divide n, right? Now, the reason I am discussing this is because if we take a look at what we did in the first and the second solution, we are starting from 1 and going all the way up to n in the first solution. In the second solution, we started from 2 and went all the way up to n minus 1, right? But if we take a look at our observation over here, checking from n by 2 plus 1 to n minus 1 is not even needed, because we know that we won't get any divisor in that range for sure, right? So based on this observation, let us discuss how we can modify the code that we have written so far so that we don't have to check for numbers from n by 2 plus 1 all the way up to n minus 1. And for that, let me quickly copy this code and then we will discuss further. So this is that piece of code that helped us in finding and printing all the divisors of n, right? Of course, we did modify it later to start from 2 and go all the way up to n minus 1. But let's take this and work on top of this. Now, what are we trying to do over here? Well, based on our observation here, what are we trying to do is we're trying to find a way so that we don't have to check for numbers from n by 2 plus 1 to n minus 1 to determine if they can divide n completely or not. Because we know that numbers between this range and including these, of course, cannot divide n completely, right? So what will we have to change in this code to be able to achieve that? Well, let's take a look at what this code is doing. This code is iterating from 1 to n, right? So if I take n is equal to 20, this code is iterating from 1 all the way up to 20. Now, if we take a look at whatever we have here, we have to skip the range starting from n by 2 plus 1 and going all the way up to n minus 1, right? So if I come back over here, it means that we have to skip the numbers between the range 20 by 2 plus 1 to 20 minus 1, which will give us 11 to 19, right? Now, the loop is starting from 1 and going all the way up to 20. But what we have to do is we have to skip 11 to 19, which means what we have to do is we have to iterate from 1 all the way up to 10, and then we also have to consider 20, right? Because the range that we are skipping is this. So how can we do this? Well, if we take n, can we say that this is 1 to n by 2 and then this one is n? We can, right? So if we find a way to iterate from 1 to n by 2 and then also consider n, will we be able to successfully skip this range, that is n by 2 plus 1 to n minus 1? We can, right? Because what are we doing is we are iterating from 1 to n by 2. And because we are stopping at n by 2, we will not be able to take n by 2 plus 1. And that is what we want, right? And the next number that we are taking is n itself. That is starting from n by 2 plus 1 all the way up to n minus 1 is the range that we are skipping, right? And that is what we want. Now, the next question is, given n, how can we do this? Well, this is pretty simple. What we can do is we can iterate from 1 to n by 2, right? And we need to take n by 2 also. So we'll say I is equal to 1, I less than equal to n by 2 and I plus plus, right? And then we will write the logic over here. And then at the end, we will consider n also. And because we know that if I take n, n will be one of its divisors, what we can do is we can just print n over here, right? So if we go by this logic, we will be able to skip numbers between the range n by 2 plus 1 and n minus 1, which is what we wanted to do, right? Now, this code can also be further optimized by starting from 2 and not 1 and handling 1 before the for loop like we did in the second solution that we discussed. So with all of this clear, let us come back to IntelliJ and let me first of all copy the name of the class that we have. Then let me create a new Java class. Let's name the class as q2 underscore print all divisors of n underscore solution 3. And what are we going to do next is we're going to have a main method. And over here, what are we going to do next is create a variable called n and initialize 20 to it. Then we can take this, right? Because like we discussed, what will we have to do is we will have to handle 1 and n separately, like we are doing over here. And then in the for loop, instead of going from 2 to n minus 1, we will go from 2 to n by 2 and including n by 2, right? So let's copy whatever we have over here and let's come back to Q2 solution 3 and paste it. And we will handle 1 separately and n separately. And we will change the loop to run from 2 to n by 2, right? And what we want is we want to consider n by 2. So we'll say I less than equal to n by 2. Now, if I take this and run this, what output do we expect? We expect the output that we got in Q2 solution 2 and we got in Q2 solution 1, right? Which is 1, 2, 4, 5, 10, and 20. So let's run the code and check. And that is what we are getting. So this modified code seems to be working perfectly fine. Now let's change this to 24 and let's see if we are getting the same output as we got the last time. And here we are getting 1, 2, 3, 4, 6, 8, 12, and 24, which is absolutely correct. And if I change the value of n from 24 to 35, I should get 1, 5, 7, 35. And that is what we are getting over here, which means that the optimized solution that we have discussed is working absolutely fine. Now, this optimized code can also be further optimized. So for that, let's come back over here and let me quickly take a few numbers and write their divisors. So if I take one of these numbers at random, let's say I take 24 and one of its divisors, let's say I take 8. And I ask you, how do we know that 8 is one of the divisors of 24? Your answer would be, it is because we can divide 24 by 8 and get 0 as remainder, right? Now let's focus on this. So this is division, and we can also write this as this, right? That is 24 is equal to 8 multiplied with 3, right? So this means that both 8 and 3 are the factors of 24. And because 8 and 3 are factors of 24, they are also divisors of 24, right? So what am I trying to conclude here is that divisors would always occur in pair, which means if you have got a number, say n, and you found one of its divisors, there would for sure be another divisor, say y, which when you multiply with the first divisor that you got, you would get n. So divisors would always occur in pair. And if we take a look at the numbers that we have taken over here as an example, and if we take a look at the divisors that we got, it will hold true for all of them. For example, if we start from 20, we've got 1 and 20, right? Then we've got 2 and 10. Then we've got 4 and 5. You take these pair, 4 and 5, it will give you 20. You take this 2 and 10, it is going to give you 20. The same thing holds for 1 and 20. And the same observation would hold for 24 and 35 also. So 124, then 212, then 38, and then lastly 46, and 135 and 57, right? So this observation can help us in further optimizing the code that we have written. So before we discuss that, let me quickly clear all of this. So to understand what code can help us in considering the pairs when we take any value of n, let's take 20 as an example. So for 20, what would we do? According to the code we have written so far, we are going to start from a certain number and end at a certain number, right? So for now, let's take the first solution that we discussed, which is start from 1 and go all the way up to 20, right? Then in each of these cases, what were we doing? We were taking the current value of I, let's say it is 1, then we were checking if n when divided by I gives us 0 or not, right? And if it gives us 0, we were printing the value of I, right? Now, on the basis of whatever we have discussed now, we can say that if n when divided by I gives 0 as a remainder, I is one of its divisors, but n by I is also one of its divisors, right? So what I'm saying is, along with printing I, we can also print n by I, right? So if we dry run whatever we have over here, what are we going to get? So we've got I is equal to 1, right? When 20 is divided by 1, it will give 0 as a remainder. So we will get 1 printed because of the first print statement. And the second print statement would print n by I, which is 20 by 1, which is 20, right? So we have considered these two. Then I will increase to 2. And this condition will be true. So it will print I, which means it will print 2. Then it will print n by I. N is 20. I is 2. So 20 by 2 will give us 10, right? So we have considered 2 and 10. Then the value of I will be 3. When I is 3, this condition will be false. Since this condition is false, these two print statements won't get executed, so nothing will get printed. Then the value of I will become 4. When I becomes 4, this condition is true, so it will print I. So we will print 4, and it will also print 20 by 4, which is 5, right? So we have considered 4 and 5. Now, if you take a look at this, we have considered all of the divisors, right? And we have reached 4 as the value of I, which means that there's no point considering the values of I from 5 onwards, right? So at 4, we will stop. Now, if we do something similar for 24, what will we observe? We will observe that if I is equal to 1, it will consider 1 and 24, right? If I is equal to 2, it will consider 2 and 12. When I is equal to 3, it will consider 3 and 8. And when I is equal to 4, it will consider 4 and 6. So here as well, going from 1 to 4 gave us all the divisors of 24. Then when we continue this with 35, I is equal to 1 will help us with 1 and 35. Then I is equal to 2 won't print anything. Same for I is equal to 3 and 4. And then finally, when I is equal to 5, we will get 5 and 7 printed, right? So for 35, we stopped at 5. Now, if you take a look at the start values, all of them starts from 1, right? But if you take a look at the last value that we have to consider to get all the divisors, they are different values. Now, the question is, given n, how do we determine where to end? As in, we know we need to start from 1, but how do we determine up to which value should I go to? And the answer to that is, I should go from 1 up to root n. Now, you must be wondering, where did I get this root n from? So for this video, let's consider that I has to go from 1 to root n, and let's not discuss about the proof behind root n or the reason behind taking root n, because if we do, we will divert from the main topic that we are trying to cover, which is solving questions based on iteration statements. But having said that, let me also tell you that the next video will be on the discussion of this magic number, that is root n, up to which we are going. Over there, I'll discuss why did we take root n for finding divisors of n. So for now, let's consider this, that if we start from 1 and go all the way up to root n, and then in each iteration, we print I and n by I. If n mod I is equal to 0, we will get all the divisors. So with this discussion done, let us come back to IntelliJ, and the first thing that I'll do is close all tabs. And then let me copy the name of this class, close this, and create a new Java class. And over here, let me name this as q2 underscore print all divisors of n underscore solution underscore 4. And here, what am I going to do next is have a main method. Now in the main method, let's take a variable, say n, and let's initialize this to 20. And then what are we supposed to do? We're supposed to iterate from 1 up to root n, right? So let's write the loop for that. But before that, what we will need to do is we will need to find root n. And to find root n, what am I going to do is I'm going to make use of the sqrt method that we have in the math class. So if we take a look at the documentation and the implementation of sqrt, it says it returns the correctly rounded positive square root of a double value. So in short, it will take a value and it will treat that as a double value, and it will return the square root, and the value that it returns will also be a double value. So without getting much into the details of the method, let me demonstrate that for you. So if I pass 16, what should I get as the output? Square root of 16 is 4. And like the method and the documentation says that it is going to return double. So we expect 4.0, right? And that is what we got. If I pass 20 instead, that is the value of n that we have right now, we will get 4 point something, right? We got 4.472 something something. If I pass, let's say 25, I should get 5. Oh, I'm sorry. I should have passed 25 over here. So I should get 5.0, and that is what I'm getting, right? Which means that math.sqrt method, that is a method in the math class, can help us in finding the square root of a given number. So let me cut this, get rid of println. Let's paste it over here and let's pass n instead and not 25. Now, what are we going to do is we're going to take just the integer part of it. So for that, we will say int. That is, we are typecasting the value that is returned by sqrt method of math class. And we'll store it in a variable, say square root of n, right? With this, we can get started with the loop. And in the loop, we will say int I is equal to 1, I less than equal to square root of n I plus plus. And what we have to do here is we have to check if n when divided by I gives 0 as the remainder or not. And if it does, what we have to do is we have to print I, right? And we also have to print n divided by I, right? So let's run the code with 25 and check the output. The output that we expect is 1, 5, and 25, right? And we got 1, 25, 5, and 5. Now 5 is getting printed twice over here because for the value of I is equal to 5, what's happening is system.out.println I is printing 5 and system.out.println n by I is also printing 5 because 25 by 5 is 5, right? So let's modify this code so that we don't get double values printed, as in we don't get a single value printed twice. So for that, what we can do is we can have two variable over here, say remainder, and for remainder we can say n mod I. Then we can also have a quotient. Here we can say n by I, right? Now with these variables introduced, what we can do is we can copy remainder, that is a variable named remainder, and we can replace n mod I with remainder, and we can replace n by I with quotient. Now, so far we have just moved the expressions to variables and we have just used those variables over here. But this won't solve the problem of the same value getting printed twice. For that, what will we have to do is we will have to check if I and quotient are equal. If they are, then print just one of them, right? And if they're not, then print both of them. So what we can do is this. If I is equal to quotient, then print just I, right? Otherwise, that is in else, we will print both. So if I run the code now, we get 1, 25, and 5, right? Now, this must have told you why did I move the expression to variables? It is because if we don't, you can see that quotient is being used in two different places, here and here. And we would have to use the same expression in both the places. And that is why I calculated it once and then stored it in a variable and used the variables instead, right? Now, let us also check for a few different values, say 20, and let's run the code. And what are we getting here is 1 and 20, then 2 and 10, and 4 and 5. If I change this to 35, we should get 1, 35, 5, and 7, right? Changing this to 24 should give us 1, 24, 2, 12, then 3, 8, and then finally 4, 6, right? So this code seems to be working absolutely fine. And this was the last optimization that we could do to print all divisors of n. So with this, let's come back over here and let's mark this question as completed. Now, let us move on to the next question, which is given an integer n, determine if it is a prime number. So before we write code for this, let us understand how can we solve this using pen and paper. And for that, let's take 11 as an example. Now, if we were to determine if 11 is a prime number or not, what would we do? we would use one of the properties of a prime number, which is a prime number is a number which can be divided by only two numbers, that is 1 and the number itself, right? Which means a number which is a prime number will only have two divisors, right? And that means that we will first of all have to count the number of divisors to be able to determine if a number is a prime number or not. And to be able to count the number of divisors, we'll have to get all of the divisors of the given number, right? And we already know how to do that, right? So what we will do is we will start from the first number, which is 1. And since 1 can completely divide 11, 1 will be one of its divisors. Now here, since we are trying to determine if a given number is a prime number or not, we will also need to count the number of divisors, right? So before we start, what will we have to do is we'll have to keep track of the number of divisors that we have got so far, right? So at this point, since we have not even started, the number of divisors would be 0, right? Now, we will start off with the first number, which is 1. And since 1 can completely divide 11, 1 is one of the divisors of 11, which means count should increase to 1 because we have got one divisor of 11, right? Then we will continue and check for 2. 2 is not the divisor of 11, right? And the same thing would hold for 3, 4, 5, 6, 7, 8, 9, 10, right? And since none of these can divide 11 completely, count will remain 1. Then we will finally reach 11. And when we reach 11, since it can divide 11, count will increase to 2, right? And at the end, for 11, we have got two divisors of 11. And since it has got two divisors, we can say that 11 is a prime number, right? Now, if we take another example, let's say we take 20. What would we do to determine if 20 is a prime number or not? Same thing, right? We will have a track of count, which will initially be 0 because we have not even started checking for any number that can divide 20. Then we will start with 1. And since 1 can divide 20, what's going to happen is count will increase to 1, right? And then we will move to 2. And 2 also can divide 20. So count will increase to 2. Then we will move to 3. 3 cannot divide 20. So count will remain the same. Then we will go for 4 and 5. And both 4 and 5 can divide 20. So count will become 3 and then 4, right? Then we will go for 6, 7, 8, and 9. And none of them can divide 20. So count will remain 4. Then we will go for 10. 10 can divide 20. So count will become 5. Then we'll go for 11, 12, 13, 14, 15, 16, 17, 18, and 19. And none of them can divide 20, right? So what's going to happen in this case is count will remain 5. And lastly, we will go for 20. And 20 can divide 20. So count will increase to 6. And at the end, we will have 6 as the count. But what we are looking for is 2 as the count. And since the count is 6, 20 is not a prime number, right? So this is how we can determine if a given number is a prime number or not, right? Now, of course, there would be a special case which I should mention, which is 1. That is, if we take 1, there's only one number that can divide 1, which is 1 itself. So count will be 1 in this case. And that is why 1 is neither a prime number nor a composite number, right? So taking all of this into consideration, what will be the code that we will have to write to determine if a given number is a prime number or not? The first thing we will have to do is we will have to get all of the divisors, which is something we have already discussed, right? Now, along with getting all of the divisors, we also have to keep track of count of the number of divisors, right? So if we go by this logic, as in starting from 1 and going all the way up to n, what will we have to do is we will have to, in the loop, keep track of the number of divisors that we have, right? So for now, let's start from 1 and go all the way up to 11 and see how we can do so. We will, of course, optimize this like we did for the case where we were trying to find and print all the devices. But let's get started with the simplest approach. And for that, let's come to IntelliJ. And over here, what I'll do first is I create a Java class. I will name the Java class as Q3 underscore determine if n is prime. And since we know that we are going to start off with the simplest solution and then we will optimize it later, let's name this as solution 1. Now for solution 1, what am I going to do is I'm going to grab the code that is there for Q2 solution 1 and I'm going to paste it here. So I've grabbed just the main method. Now over here, what are we doing is we're iterating from 1 to n, right? And if n can be divided by the current value of I, we are printing that value of I, right? Now for determining if n is prime or not, we don't have to print it, but we have to keep a track of count, right? So we will have a variable called count, initialize it to 0. And then whenever this condition is true, it means we have found one divisor of n, right? And because we have found one divisor of n, what we will do is we will increase the value of count with count plus plus. And at the end of the for loop, we will check if count is equal to 2, we will print prime, right? And if it is not the case, that is if count is not 2, we will print not prime, right? We can also handle the special case that we had discussed this way. We can say if count is equal to 1, neither prime nor composite, right? And then over here we can say else if. So if count is 1, neither prime nor composite. If count is 2, prime. And if count is more than 2, let's say composite over here, so that the message that we print over here is in line with whatever we have printed earlier, right? So with this code, let's run this for n is equal to 35 and see the output that we get. And it is saying composite, which is true, right? But if I change this to 37 instead, we should get prime. And that is what we are getting. So this code seems to be working perfectly fine. And lastly, let's also check for 1, by the way. So if I check for 1, we should get neither prime nor composite. And that is what we are getting. So this is one of the solutions to determine if a given number is a prime number or not. And like you have seen, this depends on finding the divisors of the given number and keeping track of the count of divisors of the given number, right? Now, if we take a look at the code that we have for divisors, we have got 4 different solutions, right? So the one that we implemented just now is the first solution. So let's take a look at the second solution for printing all divisors of n. And over here, what are we doing is we're handling 1 and n separately, and we're iterating from 2 all the way up to n minus 1. So let's discuss how we can optimize the code for determining if n is prime or not based on the solution 2 of printing all divisors of n. So for that, let's come back over here. Now here, what are we doing is we are iterating from 1 all the way up to n, right? But if we don't iterate from 1 and we start from 2 instead, so we iterate from 2 and go all the way up to n minus 1. That is, we skip 1 and we skip n. What should the value of count be? If you take a look at this, the value of count increased from 0 to 1 when we encountered 1. And then it increased from 1 to 2 when we encountered 11, right? So if we skip 1 and 11, that is the divisors of a prime number, which is 1 and the number itself, the count should remain 0, right? So what I mean is, let me clear this entirely first. If I take 11 and if I go from 2 to 10, if the number is a prime number, which is in this case, the value of count should start from 0 and should remain 0, right? Because the two numbers that could have divided 11 is not being considered. So if the divisors are not being considered, the count has to remain 0 for the number to be a prime number, right? And if I take 20 instead, And if I go from 1 to 20, we know that the value of count will become 6, right? Because we will get 1 and we'll get 2, then 4, and then 5, then 10, and lastly 20, right? But if I omit 1, as in I don't start from 1 and I don't go all the way up to 20, what's going to happen is the value of count will be 4, right? And the value of count being 4 indicates that starting from 2 to n minus 1, there are 4 numbers which can divide 20, right? And because there are 4 numbers in that range, it is not a prime number. So the chain that we will have to do is start from 2, go all the way up to n minus 1, and check if count is 0 at the end of the iteration. If it is a prime number. If not, it is not a prime number, right? The reason being simple, and that is we are omitting 1 and the number itself, which is what can divide a number if that number is a prime number. So even with omitting that, we have got a few more numbers that can divide the given number. That number for sure is not a prime number, right? So with this discussed, let us go back to IntelliJ. And what am I going to do first of all is copy the name of this class, which is Q3 solution 1, create a new Java class, say Q3 solution 2, hit enter to create the class, and then I'm going to copy the main method from Q2 solution 2 and I'll paste it over here. Now, if n is equal to 35, what are we doing is printing 1, then printing all the other divisors of n, and then printing n. We don't need to print anything, right? So let's get rid of the println statements. And what I mean is we don't need to print the divisors. Now, with this, what changes will we have to do? We'll have to keep track of count, of course. So we will say int count is equal to 0. And over here, what are we going to do is the same thing that we did with Q3 solution 1, which is count plus plus. If we check Q3 solution 1, we have this. Let's grab this and see what changes will we have to make to this. Now, for this code, if we assume that we are getting numbers other than 1, count will be either 0 or more than 0. We know that if count is 0, we can say that it is prime. And if it is more than 0, we can say it is composite. So here, how are we going to handle this case? That is, count is equal to 1. Then we have to say neither prime nor composite. For that, what we can do is we can keep track of count the way that we are doing over here. And over here, what we can do instead is we can say if n is equal to 1. Because if n is equal to 1, what's going to happen is this loop will never get executed. And since this loop never gets executed, count will remain 0. But what are we going to do next is we're going to say if count is equal to 0, then print prime. So if I go by this logic, it will print prime even if n is equal to 1. That is why what am I doing here is I'm handling this separately. So first of all, I'll check if n is equal to 1. If it is, then it will print neither prime nor composite. And if n is not equal to 1, then I'll check the value of count. If the value of count is 0, I will say prime. And if the value of count is not 0, that it is more than 0, I will say composite. So if I take n is equal to 1, this check will pass. N is equal to 1, so it will print neither prime nor composite. So let's run the code, and that's what we got. Now, if I change the value of n to something else, let's say 20, what would happen is the loop would start from 2 and go all the way up to 19, right? It will keep track of count. Count will be 4. And over here, n is equal to 1 will be false. So it will check the next condition, which is count is equal to 0. And since that also is not the case, that is count is equal to 4, it will go to else and print composite. So let's run the code and check. And it is printing composite. And if I change this to, for example, 23, what should happen? Count will be initialized to 0. Loop is starting from 2 going all the way up to 22. So count should not increase because 23 is a prime number, right? So count should remain 0. Then this check will fail. Since n is equal to 23, this will be false. Then this check will pass because count is 0. So it should print prime. And that is what we got. So this code seems to be working perfectly fine, right? Now, of course, there are more optimizations possible. So let's take a look at them. And for that, let's take a look at the solution 3 of printing all divisors of n. Now over here, what did we do? We started from 2 and we went all the way up to n by 2, right? And we did that because we knew that from n by 2 plus 1 all the way up to n minus 1, none of the numbers can divide n, right? So if we take this logic into consideration, what changes will we have to make in order to determine if n is a prime number or not using the solution 3 of printing all divisors of n? To understand that, let us come back over here and let's take 11, for example. Now, what are we planning to do is we're planning to go from 2 to n by 2. So if we take 11 into consideration, it will be 11 by 2. So let's take 5, right? So from 2 to 5, none of the numbers should be able to divide 11, right? Because 11 is a prime number. So what I mean is, if I take 11 and I go from 2 to n by 2, which is going from 2 to 5, and if we keep a track of count, which will be initialized to 0, 2 cannot divide 11, right? So count will remain the same. 3 also cannot divide 11. 4 and 5 also cannot divide 11. So we will stop, right? Then if we take another example, say 20, and here as well, we go from 2 to n by 2, which is going from 2 to 10. And if we keep track of count of the numbers that can divide 20, what will we get? We will get 2. So count will increase to 1. Then 3 won't be able to divide 20, but 4 and 5 can. So count will be 3. And then when we continue, 6 cannot, 7 cannot, 8 and 9 cannot, but 10 can. So count will become 4, right? So if we go by this way, count will be 4 when n is 20. So the same logic would apply that if count is 0, given number is prime. If count is greater than 0, given number is not prime, right? Because what we are doing over here is what we did in solution 2 also. It's just that in solution 2, we started from 2 and went till n minus 1. And here we are starting from 2 and going till n by 2. So we are omitting the n by 2 plus 1 to n minus 1 range because we know that none of the numbers can divide n in that range, right? So let's first of all create a new Java class. And for that, what am I going to do is copy the name of this class. I'm going to say Q3 determine if n is prime, solution 3. And what am I going to do next is close the classes that are not required. So actually, let's close all. And then let's copy the solution of Q2 solution 3. So copy the main method from here and paste over here. Now here, what are we supposed to do? Let's get rid of the println statements that's printing the divisors. And here, let's have a variable called count, right? Now, what are we going to do next is increase the value of count if we encounter a number which can divide n completely. And at the end, what we will do is what we did with Q3 solution 2. That is check for 1 separately and for all the other numbers separately. So if n is equal to 1, we will say neither prime nor composite. If n is not 1, then we will check count. And if count is 0, we will say prime. If count is greater than 0, we will say composite. So for the prime numbers, this count plus plus should never be evaluated, right? And if this never evaluates, there's no way count can increase from 0 to 1 or any other number, right? So with this, let's run the code with n is equal to 35 and we get composite. If I change this to 1, we get neither prime nor composite. If I change this to 11, we get prime. So this code also seems to be working absolutely fine. So this is the third solution for determining if n is a prime number or not, right? And for finding the divisors of n, we had 4 solutions. The last one was this one, which started from 1 and went all the way up to square root of n, right? And over here, we were printing the value of I if I and quotient were equal, or we were printing I and quotient both if they were not equal. So let's first of all understand how can we check if a given number is prime or not. using this approach, that is going from 1 to square root of n. So let's come back here and let's take 11 as an example. Now, before we talk about how to determine if 11 is a prime number or not by going from 1 to root n, let's see what would happen if we were to print all divisors of 11 using the approach that we took where we went from 1 to root n, right? So we're going from 1 to root n, which means we're going from 1 to root 11, which means we're going from 1 to 3 point something. So from 1 to 3, right? So what's going to happen is I will be 1, then 2, and then 3. So currently it is 1, let's say. Now what we were doing was we were checking the remainder. So if I is 1, remainder would be 0. And the quotient would be n, which is 11 by 1, which is 11, right? Now what we were doing was we were printing I and 11 both if they are not equal, right? So for this case, we will print 1 and 11. Then I will increase to 2. So remainder will be non-zero. Remainder will be 1. The quotient here would be 5 and we won't do anything with it, as in we won't print because remainder is 1 and not 0, right? Then when we move on to 3, something similar would happen. Remainder would be 2, quotient would be 3. And since remainder is non-zero, we won't print, right? Now, if we were to modify this to determine if 11 is a prime number or not, what will we have to do? We will have to take a variable called count and initialize this to 0, right? And I will go from 1 to 3, right? And then what are we going to do is find the remainder and find the quotient. So when I is equal to 1, remainder would be 0 and quotient would be 11, right? And since remainder is 0, what are we going to check next? We're going to check if I is equal to Q or not. If I and Q are equal, it means we've got only one divisor, right? But if they're not, it means we've got two divisors. One is I and the other one is Q. So over here, since I and Q are not equal, what we would do is we would increase the value of count by 2, right? Because we have got two divisors. So we'll say count plus equal to 2, which will make the value of count 2. Then we will move on to the next iteration. So I will be 2, remainder will be non-zero, it will be 1, quotient would be 5. And since remainder is 1, none of these would be checked. Then the same thing would happen for I is equal to 3. And at the end, count would remain 2. And since count is 2, we can say that 11 is a prime number, right? If we take another example, let's say 20, we would go from 1 to root 20, which is 1, 2, 4. And here also we'll do the same thing. That is, we will find the quotient, we will find the remainder, and what we will do is we will check if remainder is 0 or not. And if remainder is 0, then we will check if I is equal to Q or not. If I is equal to Q, increase the value of count by 1. Otherwise, this is else in case it is not legible. Otherwise, the value of count will be increased by 2, right? So what's going to happen is 1 can divide 20, right? So remainder would be 0, quotient would be 20. And since remainder is 0, we'll check if I equal to Q or not. I and Q are not equal, so count will increase by 2, which means count will become 2, right? Then we will go for 2. So here as well, remainder would be 0, but quotient would be 10. Since remainder is 0, we'll check if I and Q are equal. They're not, so count will increase by 2 here as well. So it will become 4. For 3, none of this would happen. But for 4, quotient would be 5, remainder would be 0, so count will increase to 6. And at the end, since count is 6, which means we have got 6 divisors, we can say that 20 is not a prime number. Now let's take one more example. Let's take 25 and see what would happen. So for 25, we would go from 1 to 5, right? We will have count initialized to 0. Then what's going to happen is we're going to find remainder and quotient for each value of I. So I is 1 initially, remainder would be 0, quotient would be 25. Since remainder is 0, we'll check if I is equal to Q or not. Since I is not equal to Q, we would increase the count by 2. Then I will become 2. And this will give us a non-zero remainder. And since the remainder is non-zero, we won't check further and count will not be touched. Then I becomes 3, same thing. I becomes 4, same thing. Then I becomes 5. Here remainder is 0, quotient is 5, and I and Q both are same. So count will increase by only 1, right? At the end, we will have count 3, which means we have found 3 divisors of the given number, which means that the given number is not a prime number, right? So taking that into consideration, let's write the code. For that, let's come to IntelliJ and let's first of all copy the name of this class. Let me create a new Java class and let's name this as Q3 determine if n is prime solution 4. And let's go to, Q2 solution 4. Let's grab the main method. Let's come back and paste it here. And let's modify this code. So what will we have to do is, we will have to keep n and square root of n because we need them. We also need the remainder and quotient and almost everything over here. When I say almost, I mean we don't need the println statements that is printing the divisors, right? Instead, we need a variable called count, which will be set to 0. And if I is equal to quotient, count will be increased by 1. If I is not equal to quotient, count will be increased by 2, right? So we can either do this, that is count plus plus twice, which is essentially replacing println statement with count plus plus, or we can do this, count plus equal to 2, right? Now over here, what's going to happen? At the end, we will have some value of count, and on the basis of that, we can determine if n is a prime number or not, right? So if I put 1 over here as the value of n, and I print count at the end, what do you expect? Well, we expect that we will have 1, right? Because what's going to happen is loop would start from 1, and this condition would be true because square root of n is also 1, and it says I less than equal to square root of n. So it will find the remainder, which will be 0. It will find the quotient, which will be 1. And since remainder is 0, it will go for these. So it will see that I and quotient are equal. So it will increase the value of count by only 1, right? So that means that if n is equal to 1, we will get count as 1. But if n is not 1, if n is a prime number, for example, we will get count as 2, right? Because for prime numbers, there are 2 divisors. But if we take a composite number, say 20, we should get 6. And for composite number, say 25, we should get 3. So over here, what we can do is, we can do this. If count is equal to 1, we can say that it is neither prime nor composite. Because if a number is prime, we will have 2 as the value of count. If the number is composite, we will have more than 2 as the value of count. So count will be 1 if and only if the value of n is 1, which is neither prime nor composite. So we'll continue and say, else if count is equal to 2, we'll say prime. And lastly, we will say composite. And if I run the code with n is equal to 25, we get composite. If I change it to 20, we should get composite. And if I change this to 11, we should get prime. Changing this to 1 should give us neither prime nor composite. And that is what we are getting. Now, this, of course, can be further optimized by starting from 2 instead. So if I start from 2, what's going to happen? If we have a prime number, we won't check for 1. And if we don't check for 1, it essentially means discarding 1 and 11 both, assuming that n is equal to 11, right? So if we start from 2, count should remain 0 for the prime number. And for 1 and composite numbers, count would be non-zero, right? So I'm not going to implement that optimization over here, but I highly recommend that you take this code and optimize this on the basis of whatever we have discussed just now. So with this, let's come back over here and let's mark this question as done. So let us discuss the last question from the list, which is given an integer n, print all prime numbers up to n. But before we write code for this, let us understand how can we solve this using pen and paper. For that, let's take an example, say 10. If n is equal to 10, what would be the output? The output would be 2, 3, 5, and 7, right? Because up to 10, we have got 4 prime numbers, which are 2, 3, 5, and 7. But how would we be able to determine this? To determine this, we will have to check for each number from 1 to 10, right? And for each number, we will have to check if they are prime or not. The ones that are prime gets printed, and the ones that are not prime does not get printed, right? And here we can get started with 2 instead, because we know that 1 is neither prime nor composite. So we can get started with 2, go all the way up to n, and for each number that we get in that range, we can check if that number is prime or not, which is something we already know, right? So the steps to solve this would be to have a loop which will start from 2, go all the way up to n, right? And for each loop, we will have a logic over here in place to check if the current value of I is prime or not. And how to do that is something we already know. So with this discussed, let us come back to IntelliJ, create a Java class, and I'll name this as Q4 underscore print all prime numbers up to n. And let me close this, and let's have a main method here. Now here, what are we going to do next is create a variable, say n, and initialize some value to it, let's say 10. Now we know that we will have to iterate from 2 all the way up to n. So let's have a loop which starts from 2, goes all the way up to n with an increment of 1. Now here, what are we supposed to do? We're supposed to check if I is prime or not. And if it is, we're supposed to print the value of I, right? Now we already know how to check if I is prime or not. So let me quickly put that code over here. So this is the code which would iterate over each value of I from 2 to n, and for each value of I, it will determine if that value of I is a prime number or not. And if it is a prime number, then it will print that value of I. And you may have noticed what I did was I copied the code that we have over here, right? And over here, that is in the solution of Q4, I change the occurrences of n with I and the occurrences of I with j, right? So using the same logic that we had discussed earlier to determine if a given number is a prime number or not, we can print all the prime numbers up to n, right? So if I run this code, I should get 2357 as the output, and that is what we have. If I change this to, let's say, 1, I should get nothing as the output, and that's what's happening. And if I change this to 20, for example, I should get all prime numbers up to 20. And that is what we have: 2, 3, 5, 7, 11, 13, 17, and 19. So with this, let's mark the last question also as completed. So after I had finished recording the video, I realized that I did not discuss one more solution to determine if n is a prime number or not. So let us discuss that before we end the video. Now, what do we know about determining if n is a prime number or not so far? We know that given n, we will have to iterate from 1 to root n, and we will also have to keep track of the number of divisors of n. And we were doing that in a variable called count, right? So this count variable can either have 1 as the value, or it can have 2 as the value, or the value can be greater than 2. Now, if count is equal to 1, it means that n is 1. If count is equal to 2, it means that n is a prime number. And if count is greater than 2, it means that n is a composite number. Now, I'd also mentioned that we need not start from 1 and go all the way up to root n. We can start from 2 and go to root n instead, right? So, taking this into consideration, let us discuss what will be the values of count in these 3 cases. That is, when n is 1, or when n is a prime number, or when n is a composite number. So, if n is 1, the value of count will be equal to 0. Why? Because we are starting from 2 to root n. So if n is 1, this loop won't even run. Count will be initialized to 0 and will remain initialized to 0 at the end also, right? Now, what's going to happen if n is a prime number instead? So if n is a prime number, the value of count will be 0. Why? Because the loop is starting from 2 and going all the way up to root n. So if n is a prime number, it will have only two divisors, 1 and the number itself. And if we loop from 2 to root n, we are skipping both 1 and n, which means that count, which was initialized to 0, will remain initialized to 0 itself, right? The value won't change. And lastly, if n is a composite number, what is going to happen is count will be greater than 1. And you know the reason for this already, right? So if we iterate from 2 to root n, these are the different values of count that we will have. Now, as you might have noticed, that count is equal to 0 in two cases, when n is 1 or when n is a prime number. So what we will have to do here is we will have to handle n is equal to 1 separately. And once we do that, all the other values of n will either be a prime number or composite number, which we can determine with the help of the value in the count variable. If it is 0, n is a prime number. If count is greater than 0, it should have been greater than 0, sorry. If count is greater than 0, n is a composite number, right? So keeping this in mind, let us discuss another solution to determine if n is a prime number or not. And in this solution, we won't even have to keep track of the number of divisors of n. So to discuss that, let's start off with a general integer, say n. Now, what do we know about n so far is n will either be equal to 1 or n will be a prime number or n will be a composite number, right? So if we iterate from 2 to root n, and for now, let's say that we are going to handle n is equal to 1 separately. This means that n will either fall in the prime number category or composite number category, right? So taking this into consideration and the fact that we are iterating from 2 to root n, what is going to happen if n is a prime number? Well, if we iterate from 2 and go all the way up to root n, and n is a prime number, none of the numbers in this range will be able to divide n, right? But if n is a composite number, at least one of the numbers in this range will be able to divide n, right? So can I say that when I'm iterating from 2 and going all the way up to root n, and if I find any number, let's say x, which can completely divide n, n is a composite number. We can, right? And if there's no number in this range which can divide n completely, we can say that n is a prime number. So taking this into consideration, how are we going to write the code for this? Let us discuss that. So for writing code for this, what are we going to do is we're going to take n and we're going to find the square root of n, right? These two steps will remain the same. And we will also iterate from 2 to square root of n. And the iteration will be with an increment of 1. Now, what we are supposed to do is check if there's even one number in this range which can divide n. And for that, we will have to introduce this if block. So we will say if n mod I equal to 0. Well, we are yet to decide what to do if this is true. But this will help us in checking if there's any number in this range which can divide n. So based on whatever we have discussed, what are we supposed to do is, if we find even one number, we can conclude that n is a composite number, right? Which means that there's no point or no need of checking for other numbers in the iteration, right? So how can we achieve this? Well, if we come back and take a look at this, what did we discuss was, if n is a prime number, none of the numbers in this range will be able to divide n, right? So can we say that we start off with the assumption that n will be a prime number, and we will put that assumption with the help of this statement. We will have a variable called is prime and we will set it to true. So we will assume that n is a prime number, right? And if we find an x where x is a number in the range 2 to root n, which can divide n, we will know that our assumption is false. And in that case, what are we going to do is, we are going to set the value of is prime to false. If we do this, will we be able to achieve what we are trying to achieve? Let us try run this by taking some example and understand. So if we take, for example, 11, we know that if n is 11, none of the numbers in this range will be able to divide 11, right? Which means is prime will be set to true initially, and at the end of the loop also, it will be true itself, right? But if we take 12 instead, we know that between the range 2 to root n, we will find at least one number, which you can see right now is 2, which will be able to divide 12. And since there is one number in this range which can divide n, what are we going to do is we're going to set the value of is prime to false, right? So is prime will be false, which means at the end of the iteration, we can check the value of is prime, which is false. And because it is false, we can print that n is a composite number. This seems to be working fine, right? So taking this into consideration, what will we have to do here is introduce another variable. And we will say is prime is equal to true. So we are starting off with an assumption that n is a prime number. And when we have enough evidence or enough proof that this assumption is false, we will change the value of is prime to false. And we will do that over here, right? So we'll say is prime is equal to false. And we will do this because we have found one divisor of n. Now, after we are done with this, what are we supposed to do at the end is, we are supposed to check the value of is prime, right? Now, is prime will be either true or false. If it is true, we can print prime. If it is false, we can print composite, right? So let us now go to IntelliJ and let us write the code for this and see if it is working fine for different values of n or not. So let me first of all open this class, copy the name, and let me create a new Java class. And let me rename this to q3 underscore determine if n is prime solution 5. Now, on the basis of whatever we have discussed, what are we supposed to do is take n and find its square root. So let's copy these two. And of course, we will need the main method, and let's paste the two statements we had copied earlier. Now, what are we supposed to do next is we're supposed to iterate from 2 all the way up to square root of n with an increment of 1, right? Other than this, what are we supposed to do is have a variable called is prime and initialize this to true. Now, in the loop, what are we supposed to do is check if the current value of I can divide n completely or not. If it can, what are we going to do is set the value of is prime to false. And at the end, what are we going to do is check the value of is prime. If it is true, which by the way, we can check using this statement, we are saying if is prime, and if is prime is true, it will be if true. And we know that if the condition evaluates to true, the body of if gets evaluated, right? So if is prime is true, it means that n is prime. And in that case, what are we going to do is we're going to print prime. Otherwise, what are we going to do is we are going to print composite, right? Now, we have not handled that special case where n is equal to 1 yet, but let us run the code with a few different numbers other than 1 to see if the output that it is producing is correct or not. So if I set n is equal to 5 and then I run the code, I expect the output to be prime. And if I run the code, I get prime. Now, if I change this to 15, I should get composite, right? And I'm getting composite. If I change this to say 23, I should get prime, and I'm getting prime. So this code seems to be working absolutely fine. There's one more thing that we are yet to do, and that is handling that special case where n is equal to 1. So if n is equal to 1, do we need to do any of this? No, right? So what we can do is we can cut that, have an if block where we will say if n is equal to 1, and an else block for all of the other cases, that is n not equal to 1. Now, if n is equal to 1, what we will do is we will just print neither prime nor composite. But if n is another number, that is a number other than 1, we will paste whatever we had discussed earlier. That is, we will use this logic where we are finding the square root of n and setting is prime to true and iterating from 2 all the way up to root n. And if we find even one number between the range 2 and root n, which can divide n, we will set is prime to false. And at the end of the loop, what are we going to do is we're going to check the current value of is prime. If it is still true, that means this block never got executed, which means that no number in the range of 2 and root n can divide n, which means that n is a prime number. But if it is false at the end, this means this block got executed, and that means we found at least one number in the range 2 to root n which can divide n, right? And that is why we are printing composite over here. So with this change done, let me set the value of n is equal to 1, and let's run the code and see the output. And it says neither prime nor composite. And if I set it to 4, I should get composite. Setting it to 41 should give me prime. And that is what we are getting. Now there's one last change that is left to be done, which is take a look at this for loop and the if block that is there inside this for loop. Now, what are we doing over here is if we find even one value between the range 2 and root n, such that the value can divide n completely, we are setting the value of is prime to false, indicating that n is not prime, right? So if I take 12, for example, we will iterate for 2 and 3. Now, 12 is divisible by 2 completely, right? So if I have found one divisor of 12, do we need to continue and check for another divisor? No, right? So what we can do here is, if I have found even one number which can divide n completely, I will set is prime to false, but I will also break out of the loop. So what is going to happen here is, on finding the first divisor of n in the given range, that is 2 to root n, is prime will be set to false, and the loop will stop executing anymore because we will terminate the loop from the if block. So with this change done, let me run the code for n is equal to 41 and see. It is giving us prime. And if I run the loop for example, 1, I should get neither prime nor composite. And if I change this to 42, I should get composite. Now, let me prove this part to you that the for loop is running only until it is able to find the first divisor of n between the range 2 to root n. So what am I going to do here is I'm just going to print the current value of I. So if I have n is equal to 42 and if I run the code, I get 2. Now, if I comment break out, let us see what is going to happen. I will get 2, 3, and 6. So if I don't break out of the loop, what it is going to do is it is going to continue from 2 to root n, and in each and every iteration, it will set is prime to false, which is not required, right? We set is prime to false once, and that should be sufficient. We don't need to set it to false again and again once it has already been set to false. And that is why I have put the break statement over here. So with this done, let me remove the println statement from line number 16. And this is the last solution that I intended to discuss for determining if n is a prime number or not. And with this, we've come to the end of the video. I hope I've been able to teach you something new and useful. And if you have any suggestions, feedback, or queries, feel free to put them in the comments. Thank you so much for watching, and I'll see you in the next one.